Welcome everybody! What you're seeing was captured in my living room using just a smartphone and processed through a technique called Gaussian Splatting. In this tutorial I'll guide you step by step through setting up the official pipeline and bringing this data into a real engine from start to render. This tutorial is based on the official open source implementation released by the researchers behind the 3D Gaussian Splatting paper published by the Graphdeco team. The repo is quite a bit to tame. There are a few steps and few preparation we need to take. So let's begin by installing Git. Git is a version control system that is going to be required to clone the repository and all its submodules. Head to the Git website and download the Windows 64 version and go ahead and install the software with the default settings unless you need some customization. Next, we are gonna require Anaconda. Anaconda is a popular toolkit for Python development. It provides a self-contained environment manager, helping avoiding system conflicts when installing Python libraries and dependencies. So go ahead to anaconda.com website, download the installer for Windows version 64-bit, and just go ahead and install it on your machine. There's not much configuration needed. We'll use it later to create a dedicated environment for the repo. Since Gaussian Splatting relies on GPU operations, we'll now set up CUDA to make sure everything runs efficiently later on. We'll need the version 11.8, so head over the CUDA official website onto the download archive section and download the CUDA Toolkit 11.8. Choose the Windows version, the architecture, and the installer type. I'll go with the exe. Download it on your machine and just go ahead with the installation. Choose the custom installation option and make sure that the developer tab is checked. To make sure CUDA is working, just open up a command prompt on Windows and type nvcc-version and it should return the version of your CUDA installation. Now it's time to set up our compiler. Visual Studio is what makes sure that all those low-level C++ operations can actually run. We won't be using Visual Studio Direct directly, but it's required for background operations. Head over the visualstudio.microsoft.com website and download the Visual Studio community. At this time is 2022. And just download the installer and install it. I already have it installed. The only important things you need to make sure while installing Visual Studio, it's gonna require to activate the desktop C++ workloads. So make sure that development with application desktop with C++ is active. Now let's move on to COLMAP, a structure from motion and multi-view stereo pipeline. It basically reconstructs a 3D scene from a set of photos by estimating camera positions and generating a point cloud. We'll need it later to process or input video into a camera-aware 3D representation. So head over to the official COLMAP GitHub page and scroll down to the release section and download the latest precompiled Windows release. Go ahead and unzip the file in a folder of your choosing. I usually use the user folder for ease of access because we are gonna need to make the COLMAP available system-wide. So we are gonna set up the environment system variables pointing at the right path. As you see, I already have it in my user folder. We need to point to the bin folder where the execution and the bat file are. So search for environment, edit the system environment variables, go to environment variables. On the system variable, double click on path and add a new path and just paste the path to the COLMAP bin folder. Click OK and that's it. COLMAP should be set up. Next, we'll install FFmpeg, a powerful multimedia framework that is used for processing video and audio files. In our case, we'll use it to convert a video file into an image sequence. Head over to the official FFmpeg website, select the Windows build, and choose the release from a trusted source like Gaussian.dev. Download the full release version. So once it's downloaded, extract the folder. We'll just need the files that are in the bin. So create a new folder called FFmpeg on your main drive. Mine is C at the moment. And just extract there the files that are in the bin folder. Again, we need to set up the system environment variable. So open the system environment variable, go to environment variables. In this instance, I have set up the path into the variable for the users and on system, but it's about the same. So create a new variable, copy the path from the folder and just paste it there. To try to see if FFmpeg is working, open a command prompt and type FFmpeg -version, and it should return the version of the build. Now that our environment is ready, let's move on to cloning the actual repository that contains all the code for the 3D Gaussian splatting. I'm using the Anaconda prompt here, but you can also use a standard command prompt. Head over to the original GitHub page for the repository and just copy the command to download via Git on https the repository. The recursive flag is important because it ensures that all the necessary submodules are also downloaded along with the main project. Once the download is complete, you'll have the full Gaussian Splatting repo on your machine ready to start. So cd over the Gaussian Splatting folder that was just created, and now we'll need to do some local setup and install our environment. Copy the command that is on the main page to set up distribution utilities. Then we'll just gonna create the environment that is provided with the YML file. This command reads the environment.yml file and installs all the required packages and libraries into an isolated environment. Now that the repository is ready and all the dependencies are installed, let's prepare our data. I've created a new folder inside the root directory of the project called Simply Data and dropped in a test video I recorded in my living room. Originally, this video was shot as a full 360 sequence, but I ended up trimming it down significantly. My poor RTX 3070 Ti struggled with the full workload, estimating over 130 hours of processing time, so I went with a shorter segment to keep things manageable. To extract individual frames from the video, we'll use FFmpeg, a powerful command line tool for handling multimedia. So launch a command prompt. We'll need to cd to the folder where the video is. So here I'm typing FFmpeg-I followed by the path to the video file, and this will tell FFmpeg which video to process. Then I'm adding the QScale 1 and QMin 1, which set the output JPEG quality to maximum. We want the best possible frames for reconstruction. Next is the VF-FPS, which extracts, at this time I used 4 frames per second. You can adjust this depending on your video length and how much motion you captured. More frames give better result but increase processing time. Finally, the JPEG defines the file name format. Each image will be numbered like 0001.jpg, 0002.jpg and so on. Once it's done, you'll see that the FFmpeg command have created the image sequence from your video. And this is what we'll need to generate the point cloud. In order to generate the point cloud, we'll need to put all the images in a folder called input. This will tell the command that we're gonna use next where to look for the files and how to convert them. So let's open up a new Anaconda prompt. cd over the Gaussian Splatting folder where the repo was downloaded. Then we are gonna list all our environments in Anaconda, so you can see the Gaussian Splatting is there. Then we're gonna Anaconda activate the Gaussian Splatting environment. Once activated, we can now run the Python command to convert the images into a point cloud. So type the command, then copy the path where the input folder of the generated images is, and paste it in the terminal. Press enter and it will start process all the images to create the point cloud. It will create several folders with data files. Now that we have extracted the image frames and convert them into a COLMAP compatible structure, it's time to train the model. This phase is where the actual 3D reconstruction happens. The system optimized thousands of tiny Gaussians to match the visual data captured from different viewpoints. So type the command and then paste the path where the COLMAP folder were generated. We are getting an error, we are missing CV2, that it's an OpenCV plugin, so let's pip install it before continuing. Once it's installed, we can try again with the train process. The training process adjusts the position, scale, rotation, color and opacity of each Gaussian, so that when rendered from any camera angle, the result closely matches the real video input. Depending on your GPU and the number of frames, this phase can take from a few minutes to several hours. In my case, I'm using a 37 Ti, so I had to limit the video length to keep it practical. There are two main stages to the training process. Around iteration 7000, the system produces a preliminary point cloud that's already suitable for real-time visualization and testing. This is what will later import into a real engine. However, for higher fidelity and more photorealistic results, the training continues up to 30k iterations, refining the color, position, scale and transparency of the Gaussians to match the input frame more precisely. With the training complete, we can now visualize the result using the SIBR viewer, a lightweight real-time renderer tailored for Gaussian splatting. The repository provides a precompiled version of the viewer. I'm downloading the archiving and placing directly inside the project directory to keep everything self-contained. Once unpacked, we'll use this viewer to preview the trained point cloud in real time, explore the camera poses, and evaluate the fidelity of the reconstruction before moving into a real engine. Once unpacked, let's navigate into the viewer directory, then into the bin directory, that is where the executable lives. Then I'm calling the SIBR viewer app.exe executable with the -m flag, followed by the path to output directory that contains the trained point cloud model. The -m stands for model path and it tells the viewer where to find the Gaussian splatting data it needs to render. With the viewer open, we can now explore the reconstructed scene. I'm reducing the scale modifier to get a cleaner look at the underlying Gaussian primitives, each one representing a 3D point with color, shape and orientation. As I move through the space, you can see how the splats collectively recreate the geometry and appearance of the environment captured with just a regular video. Now, let's finally transition our work into a real engine using the Xverse 3DGS plugin. This tool lets us seamlessly import the .ply file generated during training with Gaussian position, color and shape parameter directly into a real engine scene. So head over to the Xverse 3D Gaussian Splatting repository on GitHub and download the release version that matches your Unreal Engine version. In my case, that's Unreal 5.5. Once downloaded, extract the folder and copy it into the Real Engine plugin directory, which by default is located at Program File, Epic Games, the version of the UA, Engine and Plugins. If the plugin folder doesn't exist, you can safely create one. We can then finally fire up Unreal Engine, create a new blank project. I'm just calling it test. Oh, it can contain dashes. I'm deactivating the starter content, I don't need it. Once Unreal is fired up, you can head over Settings, Plugins, look up for the Xverse 3DGS plugin, activate it. Unreal will prompt you to restart, so just do so. Once restarted, you'll see that you have a new command to import the ply file. So head over to where the repository is, where we have our point cloud iteration 7000, and here is our point cloud. The plugin will create a folder with the required blueprint material and all that is necessary to visualize the point cloud. Opening up the blueprint, we see that the point cloud was correctly imported into Unreal Engine. You can go ahead and drag the blueprint on this scene. Sometimes Unreal gives this error where it loses all the texture, so head over to texting and engine scalability settings, set up to medium, and we will get back our rendering. And there you have it. The import was successful, and now we can interact with our Gaussian Splatting point cloud directly inside the Unreal Engine. This technique opens up exciting possibilities, from photorealistic virtual set to immersive VR experiences. And once the rendering issue is fixed, you can head over the settings scalability and setting up to high, and then go back to epic to have the full render quality. That's it for now. See you on the other side of the lens.